Now let's start working on this group over here. Well, again, for group B, it seems that group B is in this situation where it's adjacent to the carbon with the oxygen. That would explain why we're so far to the left over here in our peak. We're in the region of spectroscopy where we expect to be adjacent to the carbon with an electronegative element.
And is that possibly a methyl group?
Looks like a methyl group, absolutely.
How do we know the carbon attached to the oxygen?
From the chemical shift. So if you look at the chemical shifts for proton NMR, this is a good rule of thumb. If the hydrogen is attached to a carbon that's attached to an electronegative element, that tends to be absorbing in this region,
Okay.
2.5 to 5. Usually closer to 2.5, but if something's really electronegative, we can be closer to 5.
Okay.
One thing we saw is that electronegative elements tend to pull us to the left in chemical shift.
Is it like halogens, for example?
Halogens, in this case I'm using X, but it doesn't have to be a halogen, it could be any electronegative element. So basically halogens, oxygen, and nitrogen are the ones that you're likely to see. So maybe I shouldn't use an X here because this could be an oxygen or a nitrogen as well. Halogen, oxygen, or nitrogen tends to pull you to the left. Where you can get pulled most to the left if you're attached to the carbon that's attached to the electronegative element. But what if you're just adjacent to the carbon with the electronegative element? Well, then you won't be pulled as far to the left. You're likely to be in this region between 1.25 and 2.5. Make any sense?
Okay. So by having another carbon group attached, it's not as electron neutral.
Well, electronegative elements pull the signal to the left, but they have more effect when they're closer to the hydrogen. Remember that proton NMR, the absorption is coming from the hydrogen. So this hydrogen would tend to absorb in this region, between 2.5 and 5, because it's very close to this electronegative element. But this hydrogen won't be pulled as far to the left because it's farther from the electronegative element. Instead of being on the same carbon as the electronegative element, is just adjacent to the carbon with the electronegative element. So this is in this region generally 1.25 to 2.5.
Okay.
And then what about if you're on a carbon that's not connected to anything electronegative? Well, then it would be far to the right here in the 0 to 1.25 region. Now, of course, it's always possible to look up the precise absorptions on this table here. However, it's nice to have rules of thumb, so we're not constantly having to look things up in the table. So these are some good rules of thumb, but you can see this matches that. For example, notice that here we have hydrogens on a carbon that's connected to a halogen. Well, all of those are in the 2.5 to 5 region. And here we have a hydrogen that's on a carbon that's connected to an oxygen. Well, that's also in the 2.5 to 5 region. On the other hand, here we have a carbon hydrogens that are not where the oxygen is on the adjacent carbon. Well, that's in the 1.25 to 2.5 regions, as we were predicting up there. And then if there's no electronegative elements around, it's to the right of 1.25, generally speaking. Although, I see here that this tertiary is actually between 1.4 and 1.7. So these are just rules of thumb. There are some exceptions to this. These are just rules of thumb. There are some exceptions to this. When in doubt, you can just look at the table to get the precise absorptions. It's always possible that something could slightly violate these bounds. These are just rules of thumb. But in any case, that way, even without looking at our table of absorptions, these hydrogens, these two groups of hydrogens, the A and B hydrogens, they don't seem to be on a carbon with an electronegative element. They seem to be adjacent to a carbon with an electronegative element because they're both in this region. So we expect that they look something like this. The oxygen isn't on the A carbon, it's adjacent to the A carbon. And the same for this, the oxygen should be adjacent to the A carbon. So we worked out what these two fragments look like. I'm going to put in another bond here because we know there's still something this has to be attached to that we haven't figured out. So we've worked out these fragments. However, there's only one oxygen, which means that this has to be the same as this.
Sure.
So now we can put these two groups together now. What we can say is that this has a CH2 group on the right and maybe the CH3 on the left. And now we can rule out this other possibility. Earlier we were saying that group A, earlier we didn't really know what group A was. We weren't sure whether group A was two hydrogens on the same carbon or a single hydrogen on adjacent carbon, on separate There's carbons. But this actually now we can rule out. This is not going to be working because there wouldn't be enough room then for this group on this carbon. Well, that's not really true, actually. I guess that's not really true. This could have two other bonds, so I guess that still is possible. However,
we have a pi
bond.
or a ring.
Yeah, or a ring. Again, I think it's a little hard to see how we could put all these things together in a ring here. We should start to be guessing this is another carbonyl, another carbon-oxygen, and then that really rules this out over here. So if we take that leap and suppose this is another carbon-oxygen double bond, now we can put these two fragments together. We can say here we have group A on the left. No, let's call this group B on the left. And here we have group A on the right. And I have to show that there's still another bond here, that this still has room for something else to be connected to it.
So for now, we decided to put a double bond between C and O.
But the double bond, that's right. Because that would give this enough bonds. I guess we could put the double bond someplace else. However, as we were noticing earlier, this does not seem to be an alkene. Why does it not seem to be an alkene? Well, something else we talked about yesterday is that an alkene has absorptions that are to the left of 4.5. An alkene has absorptions to the left of 4.5, but nothing is in that alkene region. So that's why we're not too eager to put in carbon-carbon double bonds. It doesn't seem like we're going to have a carbon-carbon double bond because we don't have any alkene absorptions. Instead, it looks like if there's a double bond, it has to be a carbon-oxygen double bond. Let's look at something else that's very helpful to us here. Now we're starting to explain the singlets. Remember that this should be adjacent to 0 hydrogens. Well, that works over here. Can you see that this group would have a singlet because there's no adjacent hydrogens over here, no adjacent hydrogens. So that's explaining why our group B gave us a singlet. And for that matter, we know that this over here must be another carbon. This must be another carbon because that's all that's left. Well, how many hydrogens can there be on this carbon? There can't be any hydrogens because group A is also supposed to be a singlet. We know that N is 0 for all of these groups. None of these hydrogens can be adjacent to any other hydrogens. So there can be no hydrogens here. So what are the three other things this carbon's attached to?
Carbons.
Because that's all that we have. All we have here is carbons. This can't be attached to any hydrogens because if it was, there would be splitting. And we don't have any splitting here. These are all singlets. Remember, you're split when you're adjacent to other hydrogens. And if you're not split, you can't be adjacent to any other hydrogens. Now might be a good time to try to work out what's going on with this signal. What does it seem like these 9 hydrogens represent?
It could be 3 methyl groups. It could be 3 CH2 groups in a methyl group.
Now, remember, these are all equivalent.
Sure.
So it can't be 3 CH2 groups in the methyl group because then they wouldn't be equivalent to each other. It's got to be, they've got to be the same thing. So really, I don't think there's any other possibilities but 3 methyl groups. The only thing this could possibly be is 3 methyl groups because that's the only way we could have identical subunits that would add up to 9. This has to be identical subunits. We can't say that 2 of the hydrogens come from here and the other ones come from here because then these wouldn't all be giving us the same signal.
What information gives us that the 3 groups should be identical?
The fact that they're all represented by the same peak.
Okay.
If you're represented by the same peak, you must be identical hydrogens. That's something else we talked about yesterday. Equivalent hydrogens have to give you the same peak, and non-equivalent hydrogens have to give you different peaks. So all of these hydrogens have to have the same environment as each other. So really the only possibility here is 3 methyl groups. And there can't be any hydrogens on this adjacent carbon. There cannot be any hydrogens on the adjacent carbon because this is another singlet. Well, I think we can already start to see where those methyl groups are now because we've already worked out this part of the structure over here. Well, we've got these 3 places over here that are in need of hydrogens. And now I think we've accounted for the whole structure. So again, we put the jigsaw puzzle together.
You got it.
This was our group C hydrogens. notice that these really would be a singlet because the carbon they're attached to has no hydrogens. And this really would be a singlet because the carbon on its right has no hydrogens and the carbon on its left has no hydrogens. And group B would really be a singlet because the carbon on its right has no hydrogens. So the fact that these were all singlets was a very strong clue. There's not that many structures where none of the hydrogens are adjacent to any other hydrogens. If you're not adjacent to any other hydrogens, you must be connected to a carbon that's got no hydrogens on it. So there's not that many ways that we can put that structure together.